I always find the wind power equation fascinating, as in it is quite simple and it can be derived and discussed to show you the idea of modeling in physics again. So here I would like you to derive the wind turbine equation from some basic idea, which you have to think about it yourself. Before that, we have to give definition, of course, of each of these variables. So P obviously is the powered, and while rho is the density of the air. While A will be a bit more complicated. Imagine there's a turbine, and that is the area that it can cover. So let me draw a diagram. So like something like this, and then of course the turbine would turn, right? So that is the whole area that the turbine would cover. While for V will be referring to the velocity of the airflow. Okay, so probably it's the air that got drawn in to the turbine. So pause the video, try it out yourself, and I'll show you how I would do it.
2,000 years later.
Okay, so let me show you how I can do it. Imagine there are a bunch of air that got drawn in by the turbine itself with velocity of v. And you may get stuck here because you don't know what to do next. One way of thinking in physics in general, like to deal with these cases in IB, could be just think about in 1 second. So what happened in just 1 second? Because we are trying to prove power, right? But then power is energy over time. So if you can calculate somehow the energy that you can gain in 1 second, then that basically is the powered. So yeah, let's just take it as v. And because of this velocity, that basically tells you the distance that it traveled in 1 second, because velocity is meter per second, right? So then you can imagine then the air that got in through the turbine will be having a certain volume. So imagine like this is more like a 3D. I hope you can understand what I'm trying to show. More like a cylinder. So with this cylinder, then you will have the thickness of v times 1. Okay, in 1 second once again. If you want to calculate its volume, then obviously if you learn in math for sure, it's the base area times height. So the base area is simply A. Okay, so if I try to not to prove or derive, I should say, this equation directly, I can firstly say the volume of the air to be A times V, basically, right? In 1 second again. And then if you want to find the mass of the air, because as you know, density equal to mass over volume, right? So in that case, then if you rearrange this equation, that would be rho times volume equal to mass. So that means for the mass, it will be what you have in volume, A times V, times the density, rho. Okay? So that is the mass that you can find. Because if you think about how wind turbine works, is simply in terms of energy transformation. It goes from kinetic energy of the air to kinetic energy of the turbine itself. And then as you learn in generator, then it will turn into electrical energy. So basically you are trying to estimate the amount of KD in air before going into the turbine. So the energy would simply be half mv squared in general. And therefore for the m, you can just substitute the one that you find above, A times V times rho. So I'll put it down here, and then you still have the V squared, right, from the original equation. So this is simply how you can get the same equation as the one you can find on the data booklet, rho A V cube. Okay, so this is how you can prove the equation. Very simple but quite interesting. One thing, however, is when you try to use this equation, and this is the reason why I want you to derive it, is you have to pay attention to its assumption. because like I said in the previous video about the hydroelectric power, or any time that we learn in physics, assumptions are very important. If the assumptions are not met, so those are like the requirement to get your formula to be valid. If these assumptions are not met, then your equation cannot be used simply, or you can say it's not realistic. So I would like to give you some time to help me to think of as many assumptions you can think of for this equation. Pause the video, come back to us when you finish.
A few moments later.
One of the easiest way to identify assumptions would be checking the equation itself and look up what kind of parameters are involved. So here you can see there are three parameters or factors, that is rho, A, and V. So the first assumption that you may suggest is something related to the density. However, I do think that the density, if you somehow measure the density in front of the turbine, it should not vary, or you should not underestimate the density. So I don't think there is an issue with that. Okay, if you can think of anything that I don't cover in this video, feel free to put the comments in the comment section below, and I'll reply to you to see whether that assumption is valid or not. The other assumptions, however, that I do agree with is the area. So if you think about the turbine itself, the turbine must have a certain part that doesn't actually allow the wind or air to pass through. So for example, I don't think it is controversial at all that I think everyone will agree that in the middle, this tiny middle part of the turbine, you can't get the air go through it. Okay, you may still kind of argue that the blade itself is moving, so the air can still move through it. But then for this tiny part, of course, I mean you can't sure to say that area should be counted as well. So in fact, if you try to improve this model, you should take away the amount of that particular area. Okay, which in our case, I guess the A that we're referring to is simply the area of the circle, which is pi r squared. So I would say the area is not a full circle. Alright, and of course I'm just putting down a simple wordings here. You can explain in more detail. The second assumption that even more important would be thinking at the equation that we are talking about, as in for the V, is the velocity that going into the wind turbine. However, in the real life situation, the wind or the air would not stop after the wind turbine. I mean, it is literally impossible, because imagine if the air goes in with a certain speed and then after the turbine it just literally stop. It's just impossible. I mean, because those air molecules will just collide with the one at the back. So there's no way that you keep them at rest after the wind turbine. So in fact, there is still remaining KE after the wind turbine. So that wind turbine cannot obtain all the KE from it. So what you can write is the velocity after the turbine is non-zero. Alright, and then maybe you can elaborate more like what I said just now. So that is to say, if you want to really find how much the wind turbine can theoretically obtain, then you should do the calculation to minus before and after. The number 3 assumption that some of you may suggest would be simply the efficiency of the generator itself. So maybe there are things like, you may say, friction in the generator. Alright, so there will be some efficiency issue, etc. But then this, I don't think, is the most inferential assumption that we have to make, because when you try to talk about the equation P equals to this thing here, you can simply say, oh, this power is not referring to the power obtained by the wind turbine, but before or possibly can be obtained by the wind turbine. So if you phrase it that way, then the friction is something that you can talk about it later. Alright, you can of course multiply it. But then for, I would say, number 2, this one is the most inferential one. Okay, so these are all three assumptions that I can identify. If you have something else, then please leave your suggestions in the comment section below. To show you how to use this equation, let's try to do this question showing on my screen, question 20 on page 10. So try it out yourself, see how you can apply the equation, pause the video, I'll show you how I would do it. Okay, so the question tells you things like density, the speed, and then the radius. After passing through it, then the speed will reduce to this. So this is a really good question that reiterates what I said. So let's just call this V1, and this is V2, and then it sets the density also change. Okay, interesting. I think this is also true, that because when you have different speed, then you can imagine the air got more compressed or less compressed. That affects its density basically. So then it asks you to calculate the power that extracted from the wind. So this is like what I say. You may not be able to say how much power that is generated in the wind turbine directly because there are efficiency issue. But then if you rephrase it, that is power extracted from the wind, then you can just take away the assumption of whether or not the generator is 100% efficient. Let me show you a wrong example because from that you can learn even more. Okay, and I'll show you the actual answer later on. So let's say there's a student to put down the equation, so half rho a v cube, and then he or she put down, since you know the density will change and velocity will change, so he or she may just put down that density is 1.8 minus 1.2, area is 1.5. Well, this actually is radius, so area is, well, imagine it's a circle, then pi r squared, and then so let's, for the area, let's say pi 1.5 squared. Okay, and so for v, then we do x and 3, so x minus 3 cube. Okay, so let's say this is the substitution that student would do. Think about why this is wrong. Okay, I'll give you a few seconds.
A few inches later.
Okay, so the actual problem is you can't minus the density and the velocity at the same time like this. Then you may say, hey, then what if the density doesn't change? Then, okay, so let's say, how about that? Let's tweak the question. Let's say the density remain unchanged as 1.2. So what if we just keep it as 1.2? Do you think this would then be okay to calculate? The answer is not. Okay, the reason once again is because simply here. Okay, let's say again, let's say density is remaining constant. Even that, this is not okay because mathematically x minus 3 cube does not equal to x cube minus 3 cube. Okay, you should know this clearly. Imagine this is x and y. If you don't know, ask me or ask your math teacher. Okay, so that means whenever you see this kind of question related to wind turbine, never be lazy, never try to do it this way. The safest way to do it is calculate the two powers separately, so before and after. So let me show you how I would do it. So let me just erase all these things. So how you can do it is simply by finding the power extracted by the wind. What I would do is, again, we'll now restore the density. Okay, what I will do is I will apply the equation twice. So I can do rho 1 v1, rho 2 v2, right? A is the same, so I don't have to give number. So then what you can, if you really like to extract anything, then yeah, that's, I guess it's okay. Then a 12, I mean not 12, 1 over 2a, you can extract it out. And then in fact, let's just put down the number, that is pi r is 1.5 squared. And then in it, you will get the rho and also v cube. So for the first one is 1.2, v is x cube minus what is it, 1.8 and 3 cube. Alright, so then you can simply use your calculator. Then this will really be the answer. Or if you don't extract it out, that's also fine too. Okay, I forgot there is a square bracket here. So 1.2. So what I find is 3.53429. You get around, well, the calculator showed me this, nearly 2000, but I think the answer, because I kind of round up there, so I guess it's 2000 simply. So let's just take it as 2000 watts.